In this lecture, we're going to begin chapter 6 and defining what entropy is. So the entropy change and entropy balance are developed using our Clausius inequality, which, if we recall, our Clausius inequality states that the integral of our differential heat transfer across our boundaries is equal to minus sigma cycle, where sigma equals 0, we have a reversible process. If sigma is greater than 0, we have an irreversible process. And if sigma is less than 0, our process is impossible. So what we're going to do is we're going to consider two cycles, each containing two internally reversible processes. One is going to be process A plus process C, and the other one is going to be process B plus process C. So if I was to apply the Clausius inequality to the first one, I'd have the integral from 1 to 2 of dq of t for A plus the integral from 2 to 1 of dq for t for C is equal to minus sigma cycle, which has to equal 0. For the second cycle, I would have the integral from 1 to 2 of dq of t for B, plus again the integral from 1 to 2 of dq of t of C, also equal to 0. Again, sigma cycle is 0 because the cycles are composed of internally reversible processes. So if we subtract these two equations, we're going to get the integral from 1 to 2 of our heat transfer at our boundary for A is equal to our heat transfer at the boundary for B. Since A and B are arbitrary internally reversible processes that link states 1 and 2, it follows that the value of the integral is independent of the particular process that is occurring and only depends on the end states. And if we recall, if something only depends on the end states, it is a property. So we can conclude that the integral represents some change in the property of a system. We define this property as entropy, and it's represented by the symbol S. And our change in entropy is equal to the integral from 1 to 2 of our differential heat transfer for some internally reversible process. On a differential basis, our differential entropy is equal to our differential heat transfer. Again, it is defined for an internally reversible process. This allows us to evaluate the entropy between two states linked by an internally reversible process. However, since entropy is a property, the value of entropy change applies to any process, even if it is not internally reversible. So even though we define entropy for an internally reversible process, it is also valid for irreversible processes. Entropy is an extensive property, and like any other extensive property, the change in entropy can be positive, negative, or 0. The unit for entropy are kilojoules per Kelvin or BTU per degrees Rankine, and the units of specific entropy are kilojoules per kilogram Kelvin or BTUs per pound mass degrees Rankine. So where do we retrieve our entropy data? Well, we're going to retrieve our entropy data from our tables, very similarly to how we retrieved our specific volume, specific internal energy, and specific enthalpy values. The entropy for a two-phase liquid-vapor mixture is equal to our saturated liquid specific entropy plus our quality times the difference between our saturated vapor and our saturated liquid specific entropies. For liquid water, just like we can for our other properties, we can approximate the value of our specific entropy at a given temperature and pressure as the saturated liquid specific enthalpy at a given temperature. You can also make a temperature entropy diagram. It's called a TS diagram. It's useful in showing processes and cycles and also how to compare a real and ideal process. The superheated vapor region, lines of constant specific enthalpy become constant as your pressure is reduced over here. And that's where you're able to apply your ideal gas approximation. So let's take a look at retrieving some of our entropy data. For the first one, we were given water at 0.4 bar and an enthalpy, and we're asked to find our specific entropy. So I know my pressure, and I know my enthalpy. I'm trying to find my entropy. So a good place to start is I want to go to table A3, and at 0.4 bar, I can find HF. And I can find Hg. My enthalpy is greater than the saturated liquid enthalpy, but less than the saturated vapor enthalpy, which means I am two-phase. So in order to calculate the entropy, I'm going to need my saturated liquid specific entropy. I'm also going to need my saturated vapor. I'm going to need my quality. I'm going to determine my quality from my given enthalpy. So my quality actually winds up to be 0.5. So my entropy is equal to 4.348 kilojoules per kilogram Kelvin. So in the next one, we have water again. My pressure is 10 bar. I'm given an internal energy of 3.24. I'm given an internal energy of 3,124.4. So again, I'm going to go to table A3. I want to compare my value to UF and UG. I want to find that my internal energy is greater than my saturated vapor internal energy, which means I am superheated. Which means I'm going to go to table A4. I'm going to look at my pressure and look for my given internal energy, and I want to get that my entropy is equal to 7.7622 kilojoules per kilogram Kelvin. And the next one, I'm given R134A. My temperature is minus 22 degrees Celsius. I'm given a quality, which automatically means I am two-phase. So my entropy is equal to my entropy winds up being equal to 0.5969. The last one I was given was ammonia. My temperature is 28 degrees Celsius. I was given my entropy. I was asked to find my internal energy. Well, at 28 degrees, Sg is equal to 4.9948. So my internal energy is going to be equal to Ug because I'm a saturated vapor. So my answer is 1,336.2 kilojoules per kilogram. In our next lecture, we're going to introduce the TDS equations.